I'm very honored to introduce a panel that was co-organized by Dr. Puneet Chitkara, who is an executive director at KPMG India. Thank you, Puneet. This is a panel who practice and do research in making India's and the U.S. power grid reliable, economic, and very importantly, sustainable and healthy for its populations. And this is essential for both the health of the population and, of course, the health of the economy. All of the speakers apply mathematics and computers to make very difficult operations and long-run planning decisions for these incredibly complicated systems. Our four speakers are Mr. S.R. Narasimhan, who's the chairman and managing director of the Power System Operation Corporation. So I'll give him a quick introduction, and then I'll mention the other speakers. So he's an electrical engineer with an MBA in finance. Since November 18, he's been responsible for the reliable and economic operation of the All India power grid and also the connections to the neighboring countries of Bhutan, Nepal, and Bangladesh. He spent 23 years at the Northern Regional Load Dispatch Center in New Delhi and the Western Regional Load Dispatch Center in Mumbai, and then he joined the National Load Dispatch Center. He's got extensive experience in interconnection of regional grids, leading to synchronous all India electricity grid, and this has been an incredibly important and difficult task. He has handled all facets of power systems operations, from operation planning, scheduling, real-time operation, and then post-dispatch analysis to make sure the system stays reliable and runs economically. He's also implemented several electricity market reforms, and he's been a member of many Government of India expert committees. So we're very lucky to have you. So, SR?
I come in now, or you would introduce all the other speakers?
Why don't I just mention that the other speakers will be Dr. Chitkara, the co-chair of this committee, who I'll introduce in detail later. Dr. Sijia Geng of MIT, who will be joining the Hopkins faculty, and closing with Dr. Yury Dvorkin, who is on the Hopkins faculty in electrical engineering. So yeah, you can go ahead, and then I'll give the full introductions of the others later.
Yeah, thank you, Professor Benjamin. In fact, I would like to thank the Johns Hopkins Gupta Klinsky Indian Institute for having me on such a distinguished panel. Professor Hobbs, Dr. Puneet Chitkara, with whom I have had extensive interaction, Dr. Sijia Geng, Dr. Yury Dvorkin. Thank you. In fact, as Professor Benjamin introduced me, I come mainly from the electricity sector as a system operator. So I would start this discussion by focusing first on the clean electricity part of the clean energy before we move on to the other sectors. So here I just had one preliminary remark that like if you look at electricity sector in India, if we compare like 2020 21, 2 years of pandemic, we all know, but 2022 versus 2019, if we compare, where really we have got figures which are devoid of any such aberrations such as the pandemic. So what we are seeing is a consistent 5 to 6% compound annual growth rate in electricity in India, and that places enormous pressure on the electricity infrastructure. So we have two objectives. One is meeting this increase in demand, and at the same time decarbonizing the electricity sector. So unlike, like if had the electricity sector, the demand plateaued, then maybe decarbonization is a much, softer target. But now we have both the issues, and looking at our fuel base, coal is the primary source even today. So the decarbonization targets, they are indeed, they're quite challenging to achieve. So why I mention this is that, we recognize that there is a lot of discussion in other parts of the world about, electrification of the economy, electrification. When we look at the Indian context, like already we are running a race where already there's a demand growth of 5 to 6% in electricity. So any electrification of the economy would place more stress on the electricity infrastructure. So that's something which we would have to time. Be it uh, electric vehicles, be it electrolyzers, green hydrogen electrolyzers, because electrolyzer also would place a huge load on the electricity infrastructure, and we have to add more wind and solar to ensure that it remains decarbonized too. So that is the challenge with which we have to live. And at the same time, when we're talking about clean energy and the Indian context or even the global context, I feel that there are 6 priority areas that we need to address so that we can navigate this clean energy path, without any bumps, so it's a smooth ride for all of us. And the first is foremost is, of course, addressing the technology gaps through collaboration, be it advanced chemistry cells, fuel cells, electrolyzers, small modular reactors, carbon capture utilization and storage, high efficiency solar cells, you name it, and offshore wind. These are the key areas. If we have to accelerate this process of transition, how do we ensure that each of these technologies we move quickly from a technology readiness level of 3 to 4 to 8 to 9, so that we are able to use it in a widespread fashion. That's the first issue. The second, of course, is availability of low cost finance to fund this entire energy transition. And, there are various estimates. Like if you look at worldwide, we would need 150 trillion US dollars globally by 2050, and two-thirds of which would be required in developing countries. So low cost finance availability is also going to be the key. And third area, of course, is energy security and secured supply chain. I did not dwell much on this issue. Already, most parts of the world are facing the brunt of this energy security, and natural gas supplies just one thing. But even like if you look at coal, even this current war, it led to, we wouldn't even have heard about ammonium nitrate being so important, but that's required in explosives. So all our new coal mines which were under development, there was a uh, you know uh, some brakes were put on that because adequate ammonium nitrate we couldn't get. So this is just one example to show that how interconnected we all are. And when you look at wind, solar, and storage, the rare minerals such as lithium, nickel, cobalt, all this, how do we ensure that the secure supply chain of all these items? That's the third area. And from the energy security perspective, we are trying to work on, like how an interconnected grid, the One Sun, One World, One Grid initiative, which India has piloted. And we have a good experience of interconnecting all our regional grids and harnessing the diversity. So that's something on which, more work would be required. And fourth area, of course, is adopting energy efficiency and responsible consumption. That's, we cannot afford to be energy guzzlers, because I recollect my childhood days, when we actually used to sleep on rooftops at night, and the megawatt hours which we used to save by not using any electricity, we wouldn't be able to generate that much through the rooftop solar. So that's the kind of contradiction. Over the last 30 years I've seen this change. So energy efficiency and responsible consumption, of course, it's more of a challenge for a tropical country like India, with very adverse uh, conditions of temperature, and so that's something. But we need to focus on this. And fifth area, of course, is fuels for the future, like biofuels and green hydrogen. Um, uh, Definitely, I mentioned that electrolyzers, they would be a guzzler. Like when we're talking about 1 million tons per annum of green hydrogen, it would mean at least 8 gigawatt of electrolyzer capacity, and that's something which is huge. And so we'll need to add at least 20 gigawatt of solar to compensate and for this green hydrogen. So that's the fifth area. And last but not the least is ensuring that this whole transition process is just. So you would have loss of jobs in some sector, but at the same time, there's an opportunity for jobs in other sectors also. So upskilling and reskilling of the manpower, that's very important. So I'll stop uh, at this point, and then hear from the other panelists. Thank you.
Okay, thank you. We have a minute or two for questions. I'd like to remind the audience that you can put questions in the chat and we can pass them on. But I'm going to take the opportunity to ask one quick question, and we'll have a chance for more discussion later. So I'm wondering, SR, whether from the power system operator's point of view, have you detected changes in the frequency of high temperature episodes that have affected then electricity demands? And do those episodes also make having reliable power supplies even more important than in the past? So have you seen the impacts of climate change yourself, and how has it affected the importance of electricity?
Right. Yeah, certainly. That's a great question. In fact, I think in every part of the world, the system operators have experience. In India too, this last April, just about 5 months back, we had record high temperatures, one in 122-year phenomena. And that really, so if you look at, just after the pandemic, we had the third wave of pandemic sometime in January 22. And after that, when the whole economy opened up, so the demand, there was a increase in demand on that account. But this one in 122-year phenomena of high temperatures in the northern parts of the country, that led to a record increase in the power demand. And, as I mentioned about coal being the mainstay, so, and we had a situation of the coal prices also going up, the imported coal prices also going up. And that led to a stress on the resources, so we had to bring in more coal fired stations and have other governmental interventions to ensure that we have enough capacity to meet this demand. Gas, in any case, the baseline prices itself being high, our gas power plants are not, they're operating at very low utilization factors for the past many years. So we were relatively unaffected by gas prices, but imported coal prices did lead to some stress on the capacity. So this is one example. And apart from this, we have also had many instances of, record rainfall in a small pocket, which has impacted reliability and caused some amount of concern about a certain area getting flooded or the substation getting flooded. So this is something which we have been increasingly noticing in every year, some or the other pocket in the country uh, that would show up. Thank you.
So there have been climate impacts on both on demand and loads, but also on the resources that you need, whether flooding damaging infrastructure or perhaps drought affecting hydropower production. We'll return to more questions later, but I'd like to now turn to Dr. Puneet Chitkara. He's an executive director at KPMG India. He's got a PhD in economics from the Indira Gandhi Institute of Development Research. He has decades of experience with the World Bank, being a postdoctoral associate at Hopkins, many years at KPMG. He was a director at AFI Mercados. He was an associate professor at TERI University and also a senior research associate at the University of Hong Kong. So he's got around. Um, he specializes in power system management, markets, and regulation. And recently, with researchers at Hopkins, he's been looking at renewable power integration and how that integrates with the multi-state power markets that exist and are developing in India today. So, Puneet, would you like to take over?
Thank you very much, sir, and thank you very much for giving me this opportunity to be a co-panelist and make a presentation here. Uh, uh, so basically, what I'm going to talk about is the, I mean, we know that India committed to 500 gigawatt of non-fossil fuel based capacity by year 2030 uh, uh, as a commitment in COP26. So what does it mean? What are the costs of doing that? I'll just take you over this. Now, as I mentioned, that the key objectives of this are one, develop pathways. How do we get to 500 gigawatt of non-fossil fuel based capacity, including flexible assets? And with more renewable energy integration, we'll need definitely more support services in the grid. And then obviously, whatever capacity we assume in various parts of the country that is limited by the land requirements, financing requirements, and so on and so forth. And then finally, everything has to turn into an actionable plan. Yeah. Now, broadly coming to the key summary. Now, this the model that we use that was actually developed at the Johns Hopkins University when I was doing my postdoctoral fellowship there, 2019 to 2020. Now, what we get is that the carbon finance requirement for India, as was being mentioned by Mr. Narasimhan, comes to approximately 150 billion USD. And this is only required to make the transition between 2022 and 2030. And this has been computed as a difference between a scenario where the power system in India develops as usual, and as opposed to the second option is that we say that no, we are not going to develop any more coal, and we are going to go with only non-fossil fuel based generation over the next 10 years. And we see that even from a reliability point of view, India won't face any problems if coal capacities beyond what have already been planned are not added. And we can go with RE capacities, renewable energy capacities supported by storage systems. But the condition is that the renewable energy capacity needs to be added consistently. So there is a history of kind of setting targets and meeting those targets very close to, or even trying to meet the targets very close to the target year. So we need to do that consistently if we want to avoid any kind of unserved energy in the system. We do not force storage systems at certain locations, but we find in our modeling exercise that that storage systems get built in solar rich states. Another observation is, and this is kind of supported by another study which was published in PNAS last year, that though the government of India is promoting more solar as opposed to wind, but the load shapes in India and the wind profiles in India, there is from a system point of view, we find that there is a preference for wind. Then uh, uh, increasing price volatility has different connotations for solar, wind, and battery systems. So this we'll see in this presentation later, that as has been observed in other parts of the world, solar cannot afford to go merchant. Wind and battery systems can to some extent, but not solar, because we see that over years the solar prices, I mean, if they go merchant, then there is a dip in solar prices as we move into the future. Second, centralized dispatch and derivative markets are critical if we want to make uh, 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 merchant investments in some of these assets possible, because anyway merchant investments would be required, because given the fast changing technology and disruptions, uh, uh, the distribution utilities are shying away from signing long-term contracts. And also what has happened is that recently the government of India announced what is known as a storage obligation policy. So earlier we had a renewable energy obligation policy, but now they have a storage obligation policy, and which says that you have to procure, or you have to use certain storage, certain energy from storage systems where the charging has been done by renewable energy sources. Now, what we find in our simulations is that when the system on its own requires storage systems to be there with high renewable energy integration in the future, then solar systems are naturally viable. But when we force this obligation, when we make this a constraint in the model, what happens is that at least in the initial years, what we find is that there are renewable energy assets which come up and which kind of charge batteries, and electricity just gets cycles through these battery systems before being consumed. So so this is kind of slightly an inefficient outcome that comes up in the initial years. And but after 2026, we find that the storage systems behave very naturally as they should. Now, model description, obviously we have modeled entire India. It has more than 1,000 generators. I mean, obviously we have kind of, I mean, each state in India, including the neighboring countries, have been lumped into zones connected by transmission lines, 18 representatives per year taken, 10 years, and the standard expansion planning model along the lines of Jasmine. In fact, exactly along the lines of Jasmine, with all the unit convexified unit commitment constraints there. Some scenarios that we had built was that we said that, okay, we'll have scenario one where we won't have any RE or a renewable energy policy, like we need to have 500 gigawatt by 2030. We'll kind of relax that, and no demand shifts allowed. So in this model, what we have done is that we have also kind of allowed the states, individual states that have been modeled, to shift their demand across the day while kind of maintaining the energy levels that they need to serve. Then the
Puneet, in the interest of time, I'm wondering if you could wrap up, and if we can get back to this later, we will. But
yeah, sure. So yeah. So basically, what I'm coming to is, I mean, these are the, I mean, obviously, so in the expansion planning model, we get all these results, which obviously we can talk about. But RE policy could help meet NDCs, the nationally determined targets that we have. 50% of the energy can be met from non-fossil fuel sources, but this requires, as I mentioned, a carbon finance of 140 billion USD. Storage policy not really efficient in the initial years. Then I wanted to, and this kind of shows up here where you see I've mentioned this BESS RE. BESS RE is basically storage systems with charged by renewable energy. And in the initial years, we find that their utilization is 42%. Actually, this is artificial because renewable energy is being just passed through the batteries and then consumed. And over years, this kind of converges with the normal 4-hour battery utilization. It kind of comes to that. And this is seen across scenarios. And in terms of prices, we see that the prices kind of keep on, I mean, you see this price close to zero, which is the darkest region in the afternoon. So this band keeps on increasing over years. And this is the time when solar generates, and then you can see that there is some wind generation. Wind generation happens normally during high prices, and then battery charging also is kind of helpful. So basically, conclusions are phasing down of coal requires a carbon finance of so much amount, leads to a emission reduction by 20%, and it would help to hybridize solar, battery, and wind if the owners of these assets want to go merchant. And then as we discussed, that wind is more naturally suited for the Indian grid as opposed to solar per se. And battery systems are being encouraged by the government now, but one could wait for the prices to decline over years and for more RE to pick up. Thank you very much. Yeah.
Thank you, Puneet. I would love to do a deep dive on what types of emissions are going down, how that might help air quality in India's cities. But I hope we get another opportunity. I'm sure we'll get another opportunity to do that. At this point, I would like to pass the virtual podium to Dr. Sijia Geng, who will be joining the Hopkins Electrical and Computer Engineering faculty in January. She's now a member of the MIT Laboratory for Information Decision Systems, where she's a postdoctoral associate. Her PhD is from the University of Michigan, and she's also worked at Pacific Northwest National Lab. So, Sijia?
Okay, thank you very much for the kind introduction. Let me share my slides. Yeah, okay, so hello everyone. First of all, thank you all for joining this discussion today. And thank you the organizer for making this conference happen and inviting me here. In this presentation, I will talk about challenges of integrating renewable resources to complex energy systems from analysis and control perspectives. You will notice a lot of echoes with the previous two speakers, and I'm sure also Dr. Yury Dvorkin later on. So let me start by saying just a few words about myself. So as Ben mentioned, I'm an incoming assistant professor at Johns Hopkins, and currently I'm wrapping up my postdoctoral work at MIT on optimal infrastructure planning for electrified transportation systems. And before that, I did my PhD in University of Michigan, working in power system analysis, control, and optimization. The central theme of my research is to facilitate the energy transition to renewable resources and ensures an autonomous, reliable, and clean future energy systems. Yeah, so as Dr. Narasimhan, forgive my pronunciation, increasing electricity demand together with retirement of coal-fired power plants is forcing power systems to operate ever closer to their feasibility limits. So integrating these cutting-edge renewable technologies into power systems will help facilitate the clean energy transition. However, there are several fundamental theoretical challenges as well as practical societal concerns when integrating renewable resources in large scale into power systems. Due to time limit, I will focus my discussion on the theoretical challenges. From a system and control perspective, I wish to highlight what I see as the two major issues that are arising with the high penetration of renewable generation. The first one, which I believe the audience will find familiar with, is the uncertainty inherent in renewable generations, such as wind and solar. Such uncertainty poses great challenges to the operation of power systems because the fundamental operating principle of a power system is that the generation must equal to the load at every time instant. Therefore, it demands careful analysis to ensure the stability and safety of power systems under uncertainty. And some of my previous research has been devoted to quantify the impacts of uncertainty on power system dynamic behaviors. So secondly, unlike traditional large synchronous generators, renewable resources are often small in capacity and are connected to the system in a distributed manner, leading to hundreds of millions of uncertain control points in the future. The current centralized control schemes will soon become obsolete as more and more distributed renewable resources are being adopted. Therefore, one direction of my research is to develop novel distributed and decentralized control strategies to coordinate numerous renewable generation that are deployed across power systems. In what follows, I will mention some of my own works on constructing distributed controllers. As illustrated in the upper left figure, nowadays many solar PV inverters are interspersed with unbalanced loads, and without proper coordination, they might negatively affect the health of the system. The first control strategy utilizes the existing solar photovoltaic inverters to reduce the three-phase voltage imbalance in distribution networks. The proposed distributed control schemes subdivides the network into disjoint partitions and only needs local communication within the partition. The advantage of this controller is that it fills up the gaps in previous technologies and is able to deal with uncertain loads that are time varying and potentially with unknown location and magnitude. Most importantly, rigorous stability guarantees are provided, ensuring robustness in practical environments with uncertainties and disturbances. Note that this work focuses on a specific objective of reducing voltage phase imbalance. More generally, a wide range of safety constraints can be considered due to various engineering constraints, such as voltage magnitude limits, power flow limits, inverter current limits, and so on. Referring to the bottom right figure, which gives an example of a power system that accommodates many distributed wind turbines. A second control strategy is designed for inverter interfaced renewable resources and satisfies generic safety constraints by construction during transient dynamics. The control schemes again offers a distributed structure which has important practical value. So far, I've highlighted two major challenges with the integration of renewable generation that are the uncertainty and the distributed topology. On the other hand, I'd like to remark on the brand new opportunities brought by the integration of renewable generation. Specifically, next generation local community-based energy systems are becoming technically and economically feasible as the technology advances. In the past, I've worked on the optimal design and operation of microgrids and energy hub systems, mainly focused on managing the uncertainties in local renewable generation to satisfy the demands, yet balance the reliability and investment cost. The left figure illustrates a multi-energy hub system that relies on local renewable generation along with storage devices to achieve full controllability and flexibility. In longer term, we are really envisioning a highly interconnected energy system across sectors, From one of my current projects at MIT, I considered a couple distribution systems and transportation systems as shown in the right figure. I aim to design the charging and refilling station and the electric bus fleet to supply future transportation demands. Within the station, various distributed energy resources can be considered, especially hydrogen-based technology and storage. Finally, I would like to conclude my presentation by pointing out that as large synchronous generators are replaced by millions of smaller inverter-based resources, there will be profound implications for power system dynamics and operations. This creates lots of open questions, including modeling and stability analysis, which will play critical roles during the energy transition. With that, thank you again, and I will be happy to answer questions and hand over to Dr. Dvorkin.
Okay, thank you, Sijia. And I'm sure that if we had time, that Mr. Narasimhan would have a lot of comments about the practical challenges he's facing as he's looking at getting 500 gigawatts of renewables on the grid by the year 2030, and it'd be interesting to know how much of that would be local. So we'll go to our last speaker now, who is Yury Dvorkin, who's an associate research professor in electrical computer engineering and civil and systems engineering at Hopkins. He uses applied mathematics, operations research, and economics to help accommodate challenges both in operations and in planning posed by both renewables and emerging smart grid technologies. Very appropriately, for this meeting, his dissertation, which was called Operations and Planning in Sustainable Power Systems. In 2016, he won the award for the first University of Washington Clean Energy Institute's Scientific Achievement Award. Between then now, he's been a professor at NYU, and he's just joined the Hopkins faculty this last summer. So if you could take about 6 or 7 minutes, Yury, and then we'll pass on the baton.
Thank you, Ben. I'll try to be very quick, and what I'm going to talk today is how engineers could help quantify and alleviate effects on public health that arise from the power outages. And I'm not a public health expert, so I'm going to focus on the engineering side of things, and I will allude where it connects to public health. What we did, we realized that in order for us to be able to pinpoint how public effects of power outages can be studied, we need to have granular and nearly streaming data. And we realized that there is no source of this data. So what utilities do, they present a snapshot of outages that happen right now, but they don't present it in a machine-readable format, so nobody else, including emergency response agencies, can take this data and analyze that. Another problem that happened is that because they only present snapshots, there is no archive data, so you cannot run some even very simple data science operations over this array of data and extract or retrieve some patterns. So what we decided to do, we use a publicly interfaced Conedison outage map. And before any questions arise, I can say that similar outage maps exist in other cities in the United States, and they work on the same principle. They just show you where contingencies are located, and all of the data is hidden under the hood. So we designed a crawler that helps you collect this data in real time. And we focus on New York City, and we were able to connect this streaming data through our crawler to a data set of social demographic data. As a result of it, what we were able to do, we were able to connect power outage location and impact and connect this to the particular social attributes of the locations that these outages affect. And one of the things that we learned in the process was the fact that we can pinpoint locations and time to a very high resolution. So in terms of the space, we can have an exact street address, and we can have an exact temporal stamp, which we estimate with a precision of 20-30 minutes based on the sampling rate that our tool uses. And you can see this dashboard, which represents the outages in New York City, which I took last night at a certain time in the evening. And what you can see are the labels with different colors. And different colors represent different levels of electricity vulnerability, which we could roughly interpret as different priority for repair. Obviously, right now we have a clear sky day in New York, so these are fairly few outages, and there is not much pressure to distribute scarce repair resources in some kind of priority order. But in case of large outages, it's very important to have an idea of which outages needs to be repaired first, and that's what this ranking algorithm does. So in that particular setup, one of the most important things that we were able to do is not only that we can collect the streaming data, we can also create an archive which aggregates this data across time, and we have more than 1.5 years of data. And we were able to analyze it across different zip codes in New York City, and that's what you can see here on the left-hand side diagram, which on the vertical axis has the number of outages, and on the horizontal axis has different zip codes in New York City. So what you can see here is that the number of outages, despite the fact that all of the service territories are being in the same tariff zones and being regulated by the same tariff, they essentially leads to a very broad dispersity of outages across both different parts of New York City, different boroughs, but also within each borough, there is a high variability in terms of the outcomes. Not all of these outcomes can be related to socio-demographic features. Some of them are explained by the power grid nuances. For example, in Manhattan, there are more underground lines than anywhere else in the city, so they are less prone to outages during nasty weather. On the other hand, what we can observe despite this technical difference is that the main drivers for a higher number of outages is the income and demographics. They are also responsible for a higher variability within each borough. Another important thing that we can exploit from this array, and that is the data that is being streamed from the local utility, is causation. So we were able to correlate external factors, weather, to the outages, and also to the causes of the outages. And what we were able to observe that we don't have very accurate data on what causes this problem because they're not being recorded. What you can see here is that the largest attributable effect is weather related. But the second from the right column says still investigating, and this is the data which never gets reported. So missing data prevents establishing a clear correlation between a causation and between the effects of the outages, which is a huge gap in knowledge because without knowing what causes an outage, there is no way for preventive action. And I would like to share more ideas about this project, but considering the time limitation, I'm just going to overview the next and ongoing steps. We want to leverage this outage data to inform energy transition planning because whatever solutions are available there, and these are the solutions that the previous colleagues described very clearly, distributed energy resources, community-based microgrids, renewables, they can help alleviate these disparities. And at the same time, they can help to improve reliability. So what we want to do, we want to integrate this information about the outages into planning tools for energy transition. And do I have a minute, Ben? Or...
I think I'm supposed to pass it on to the next panel on
okay.
Climate and health. So I think we need to conclude. I wish we had another hour because there's so many connections we could make between the different talks from the local level to the continental scale, sustainability and the relationship to human health and reliability. But I hope that we'll be able to do this again next year. So at this point, I'd like to pass this on to Ben Zajcik and Nitish Dogra, who are going to be having a panel on climate and health.